Okay, second video on collisions. We're going to look at momentum. First of all, what is it? It's just a measure of how difficult it is to change the motion of an object. That's it. Physically or mathematically, if you're to define it, momentum is mass by velocity. It's a scalar by a vector, so it's a vector quantity. And also, when you're filling in for the velocity, fill in the I and j components. So let's have a look at two examples. If you're a rugby player, that rugby player can run fast. He's got a big mass. So as he runs, he's got a big momentum. And it's quite difficult to stop him. So you need another similar sized rugby player with a similar momentum to make his momentum halt or stop. If we put that rugby player against the little child there you can see is a bit unsteady on its feet. The velocity that the child is moving at is probably quite low. It's got much less of a mass. So if you multiply its mass by the velocity, the momentum is much, much less. So that's an idea of what it is. And just a reminder of what I said. Momentum is a vector quantity. Velocity, you're going to have to fill that in IJ form. And the units there are kilogram meters per second, just like impulse. Now, we're not really interested in the momentum of a single object. We're more interested in what happens when the objects collide. So when the rugby player hits the child, for example, what actually happens? Well, when they hit, some of the momentum of each of them will be lost. So if the child hit the rugby player, you'd expect the rugby player to slow down a little bit. Very little, but he would still slow down. So some momentum would be lost. Likewise, the child is going to the left, and he has a little bit of momentum going to the left. If the rugby player hit him immediately after the impact, the child would probably be going to the right. So that child would have lost some of its leftward momentum, which is another way of saying either slows down, comes to rest, or it ends up traveling to the right. Okay, so let's have a look at Newton's laws again. We have the two trucks, they collide. So we're looking at the point of collision here. And what we know is each of them experiences an impulse. So the impulse is the change in momentum for both of those. We know from Newton's third law that each of them will experience an equal and opposite impulse. So if I fill in the MVs and MUs in there, I get that. And then when I rearrange it, I get this formula. And that's a very important formula for this topic. It's called the principle of conservation of momentum. Okay, quantity-wise, M1 is the mass of the first object, M2 is the mass of the second object. U1 and U2 are the initial velocities of the first and second object. They're the velocities before the collision. V1 and V2 are the velocities after the collision. So what this is saying is the momentum of the two trucks beforehand should be equal to the momentum of the two trucks afterwards. So if one truck hits the other, then the total momentum going in should be equal to the total momentum going out. That's why it's called the principle of conservation of momentum. All right, so there's the written definition. In any collision between two or more objects, the total momentum before equals the total momentum after, so long as no external force acts on the system. And what we're really talking about there with the last part, no external force, the objects collide, we're assuming that the engines are turned off and that there's no friction. So they just collide, and depending on the masses and the velocities of either object, what could happen is they could both rebound. What could happen is they could both end up traveling to the right, they could both end up traveling to the left. Or maybe what happens is they stick together, they coalesce is what that's called, and they end up traveling to the right. So we don't quite know what's happening because we don't have any data yet. And again, that's my formula. Now, a couple of things there. The velocities are vectors, so the direction needs to be included, either in IJ form or just with a simple positive and negative. You'll see I use the IJ form here. All right, so let's have a look at a couple of examples. In this case, I have a small ball and a large ball. Look, the small ball is of mass 0.5, large ball 1.85. I'm going to leave them collide off each other, and the momentum before should be equal to the momentum after. So right now we have a big momentum to the left, small momentum to the right. So the net momentum is going to be to the left. Play. If we look here then, what happened is he travelled off at a larger velocity to this guy. But if you subtract those two momenta, the total momentum there would have been equal to the momentum beforehand as well. Okay, let's see what happens if they're equal mass, but we can see this guy is going to move at a larger velocity. So bigger momentum for the light blue one than the pinky purple one. So the total momentum before should equal the total momentum after, and we see that's kind of the case there. Okay, let's make this guy very, very small. So the total momentum before is the net momentum there. It's going to be to the left, and that should be the same then afterwards. And we can see in that case that his momentum was so large, or his mass was so large even, that what happens is after the collision he keeps moving in that direction. And if you added the two of those together, the total momentum there would be equal to the total momentum before the collision. So subtract those, total momentum there equals sum of those total momentum after. Okay, let's have a look at a few questions. Number 1. Car mass 800 kgs is moving at 20 meters per second. It collides with another car of 1500 kgs, which is at rest. They stick together. Find the initial velocity after the collision. So we're going to use that. The first thing to note here, I'm going to say car 1 is the 800 kg car. U1 is equal to 20. So its momentum will be 1600. The momentum of the second car beforehand is 0 because it's at rest, because U2 is not. And then afterwards, if the two stick together, V1 and V2 are equal. So we get that. I can add the right-hand sides then, and I'll get 2300 by V. And then if I divide under by the 2300, I'll get a value for V. Note as well, I've put in the U1 as 20I. So V works out as 6.96I, which should make sense. If a car is moving with a certain speed and it collides off another car that was at rest and they stick together, the speed afterwards should be decreased because of the two masses being combined. They've got a larger mass afterwards than they have before. Question 2. So we have a 6,000 kg mass traveling at 10 meters per second, catches up with another one that's moving at 2 meters per second in the same direction, but it's got a mass of 2,000 kgs. Now it gets coupled together, so it sticks together, and they've got the same final velocity as well. So M1U1, 6,000 by 10, M2U2, 2,000 by 2. Both of those have got the same sign because they're in the same direction. And then V1 and V2 are equal. I put in the I and J, or the I's into it, and then when I simplify that, I get 8I. And that would make sense direction-wise. If they're both going to the right, when they join together, they will end up going to the right as well, with a velocity somewhere in between the two of them. Third example. Similar to the previous one, but the second object is moving to the left now. So we have a 6,000 kgs moving with 10 meters per second to the right, we'll say. And then there's another carriage of mass 2,000 kgs moving to the left. So we'll have to put a minus in there with the 2. They collide and couple together, so they stick together. So V1 and V2 are equal in this case. So look, I've got plus 10I and minus 2I for the opposite directions. And the velocity there works out as 7I. Again, should make sense because the heavier mass with the larger velocity is going to dictate the final velocity more than the other one. So we end out going in the same direction as the heavier particle moving at a quicker speed. Okay, pause the video and do that, but I'm going to keep going. Okay, this is a slightly different question. So we've got a gun of mass 2 kgs fires a bullet of mass 10 grams with a velocity of 400 meters per second. Find the initial recoil velocity of the gun. It's unique in that the gun and the bullet are together at the start and they're at rest. So the momentum before is actually equal to 0 because they're at rest. Afterwards, what ends up happening is the bullet comes out one way and then the gun has to go back the other way to keep the net momentum equal to 0. So we have that value. So initially, the velocities U1 and U2 are 0 because they're at rest. And then after the bullet is fired, its mass is 10 grams, so 0.01 by 400I. So we're saying that the bullet is going to the right. And then we have 2 by V for the momentum of the gun. And then when you solve it, you get V is equal to minus 2I, meaning that the gun is going to go in the opposite direction to the bullet, which is referred to as a recoil velocity. And I'll show you a few videos on recoil velocity in a moment. Okay, for you guys. Will you do those questions? Okay, end of second video.